Welcome to the debate. We are witnessing, I think it's fair to say, arguably the most intense technological race of the 21st century. The quest to build a functional, truly large-scale quantum computer. But what really dictates the outcome of any revolution isn't just raw power, right? It's how successfully we conquer the fundamental limitations. And in quantum computing, that limitation is noise, or decoherence. The hidden pattern we're looking at today, the one that's going to define the winners and losers here, is that the leading solutions fall into two, fundamentally opposing architectural philosophies.
Absolutely. And this isn't just some, minor technical disagreement. It's a really profound strategic choice. And the central question facing the entire field boils down to this. Which path, the incremental performance scaling route, the one we see with superconducting chips like Google's Willow, or the, let's call it, paradigm-shifting built-in error immunity promised by topological qubits like Microsoft's Majorana one approach, which one offers the most viable, the most imminent path toward that big, useful machine we all need?
And I'll be arguing that, history often suggests optimization comes before the big revolution. The immediate verifiable success, the established engineering path we see with performance-scaled superconducting chips, specifically the breakthroughs with Willow, that offers the clear way forward. This architecture has already moved quantum computing out of just theory and into, practical, reproducible applications today.
And I'm going to contend that this specific race actually demands a more radical approach. Look, incremental improvements just can't overcome a scaling barrier that grows exponentially. The fundamental flaw, this massive overhead needed for error correction, can only really be solved, I believe, by the topological approach. It changes the rules entirely by offering resilience right at the hardware level. We're looking at a system where quality, not just sheer quantity, becomes the deciding factor. This is the kind of insider knowledge, the hidden pattern that really separates successful scale-up from just, perpetual prototyping.
Right. So the path to useful quantum computing isn't some distant dream. It's actually being paved right now through rapid, structured engineering optimization. When we look at the Willow chip, we see Google has taken quantum computing from this sort of esoteric science into the capability of doing science with it right now. And the most critical metric, I think, showing this success is quantum coherence time. How long a qubit holds its delicate state. Willow dramatically increased this by a factor of 5. It jumped from 20 microseconds in their previous chip Sycamore up to 100 microseconds. That's significant. And this is more than just, a simple performance boost. It really proves the viability of the whole engineering pipeline. Crucially, this system is now successfully operating below the critical quantum error correction, the QEC threshold. That's a game-changing milestone. It means the theoretical framework for fighting noise, it's actually functional now. We're achieving exponential suppression of error rates as we scale up our surface codes. That's the geometric layout used to protect the quantum state. And here's probably the most important data point. Logical qubit lifetimes. They're now longer than the physical qubits they're made from. This means we finally managed to beat that physical, localized noise through extraction. It results in reproducible, actionable success.
Okay, I see why you emphasize that verifiable success. And look, those performance gains are indeed remarkable, no question. But that perspective, I think, misses the fundamental flaw that's derailed so many optimization-only approaches in tech history. It's the debilitating overhead required to constantly fight the noise that your fragile physical hardware inherently generates. Let's just quickly define terms for everyone. A physical qubit is the actual hardware piece, like a superconducting circuit in Willow, and the logical qubit is the single, stable, effectively error-free unit we actually need for computation. The problem is just one of massive redundancy. Current leading systems like Willow, they need hundreds, maybe even thousands of these very fragile physical qubits just to stitch together one stable logical qubit. This is what I sometimes call the football stadium problem. You end up needing millions of physical components, all needing to be cooled to temperatures colder than deep space, occupying huge infrastructure, just to build one truly useful machine. Incrementally improving inherently fragile hardware just makes the complexity and that physical overhead worse. The topological approach, though, it flips the script entirely. It relies on a, frankly, radical new state of matter using what are called Majorana zero modes. These are particles that are their own antiparticles. Instead of storing the quantum information locally in one fragile physical bit, the information is distributed, it's woven into a global property across a whole surface. Think of it like this. If your quantum information is stored in a single, delicate glass vase, that's your physical qubit, any slight vibration shatters it. The topological approach spreads that information out, more like ripples in a pond.
This provides hardware protection built in at the ground level, as they say. It makes the qubit naturally immune to small, local errors, stray photons, vibrations, things like that. This could potentially eliminate the need for that massive QEC overhead, accelerating the path to a functional device by prioritizing, quality of resilience over just brute force quantity.
I see why you think that QEC overhead looks insurmountable, but let me offer a different perspective here, one grounded in the actual data, the consequences of what we're seeing. Willow's successful suppression of errors proves that QEC is working effectively and that the engineering path is sound. That exponential suppression, where the error rate literally halves each time we increase the distance of our surface codes, like scaling from distance 3 to 5 to 7 codes, that's a direct, measurable result of this approach. We are mastering redundancy, we're making it efficient, and furthermore, we're constantly tuning and optimizing these systems. The tunability of our superconducting qubits allows researchers to continuously develop new calibration strategies. This helps mitigate the outlier problem, the tendency for just a few bad qubits to spoil the whole computation, and ensures reproducible high performance across the entire device. You might call it complexity. I see it as a manageable, evolving engineering challenge. The point is, we're producing real results now, not waiting for some contested breakthrough in fundamental physics.
That's an interesting point, though I guess I would frame it differently. While Willow's performance on certain benchmarks, like random circuit sampling, is mathematically just mind-boggling, demonstrating a calculation that would take something like 10 to the 25 years on a classical supercomputer, it still relies on constantly battling the environment. That success comes at the cost of cooling these systems down to 50 millikelvin. That's hundreds of times colder than interstellar space. The very necessity of that extreme cooling demonstrates just how fragile these systems are, how non-local the problem really is. And this, I think, is the hidden strategic pattern that really matters. In these highly complex, noise-sensitive systems, fighting the symptom, the decoherence, with just massive redundancy, it quickly becomes uneconomical. It inherently limits your scale. If you have to keep cooling a whole football stadium's worth of components, eventually the power budget and the physical space required just paralyze you. The topological approach strategically shifts the goalpost. Instead of fighting noise with layer upon layer of engineering complexity, you design a system where the noise simply doesn't matter as much, because the information itself is non-local and inherently rigid. It's an intellectual leap, really, that could transform this logistical nightmare into something more like a controllable production process. I'm sorry, but I just don't buy that the current scaling path is the fastest or the most efficient way in the long run.
This is where that sort of insider knowledge, understanding the deeper pattern, becomes crucial. Microsoft claims that once the fundamental topological science is unequivocally validated, moving beyond the scientific uncertainty into solid proof, the entire scaling problem shifts dramatically.
It changes from needing, as they put it, 5 miracles to cross, these fundamental science breakthroughs in materials and physics, to becoming a purely predictable engineering problem, maybe something more like chip fabrication today. If that's true, it drastically changes the expected timeline. They predict this shift could accelerate the path to a functional, fault-tolerant computer down to potentially just a few years after that validation. If they're right, solving the noise problem at its core provides this unique, potentially exponential competitive advantage in the race to scale. It could make the current incremental improvements look like, maybe a tactical misstep in the grand scheme.
Okay, that's a compelling argument based on, let's say, optimism about fundamental breakthroughs and the promise of a simpler engineering curve down the line. But have you really considered the immediate, very palpable risks involved? We are operating based on verifiable evidence right now. The topological approach, by contrast, is still built on fundamental science that remains, frankly, contested and incomplete. Just think about the Nature publication around the Majorana launch. It generated significant controversy precisely because the paper did not provide clear empirical evidence of a topological qubit actually functioning. Specifically, it lacked essential measurements like coherence times or unambiguous evidence of topological braiding. This led to some serious skepticism in the physics community. Look, we can't rely on hope for an unvalidated breakthrough when verifiable functional quantum advantage is already being achieved by existing technologies that are being scaled and continuously tuned. We have to stick to the evidence, to reasoned, measurable progress. The risk of sinking billions into physics that might just prove infeasible is simply too high when a proven engineering path already exists. And let's talk about utility, because that's the immediate competitive edge. The utility of this performance scaling route is here now. Willow's success in running the quantum echoes experiment provides a valuable, real-world tool for understanding complex quantum systems. Specifically, it enables high-fidelity simulation and can augment techniques like NMR spectroscopy for studying molecular structure, which is critical if you want to design new proteins or, say, advanced battery materials. This ability to model molecules at the quantum level, that's precisely what digital computers choke on. Classical simulation just becomes too resource-intensive beyond maybe 23 or 24 orbitals. So this is a real-world application today already transforming fields like material science and chemistry. We're delivering impact now, rather than waiting perhaps a decade or more for the final, perfectly fault-tolerant machine.
I guess I come at the definition of utility from a slightly different angle. While near-term utility is significant, for research absolutely, the ultimate competitive advantage, and let's be honest, the reason this multi-billion-dollar revolution matters so much, is to solve the truly grand challenges. We're talking about potentially developing room-temperature fusion power or tackling problems requiring immense complexity, maybe even a theory that unifies all the forces of the universe, the kind of theory that eluded Einstein.
Right.
And these goals require massive, perfectly accurate, fault-tolerant machines capable of running for days, maybe even weeks, without a critical error. The inherent delicacy of those physical qubits, even with heroic error suppression efforts, means scaling to the required magnitude for these profound scientific breakthroughs will always be inherently limited by that constant need to police the redundancy. Topological stability, I argue, offers the true pathway to the ultimate computer, one exceeding the power of any digital computer without that constant looming threat of catastrophic decoherence wiping out the entire calculation mid-run. You have to build the final structure stable from the ground up, not try to endlessly patch stability onto a fundamentally fragile foundation.
So, to summarize my view, we have shown that the performance scaling route is producing immediate verifiable results. It's demonstrating huge superiority over classical supercomputers on specific tasks and moving us toward near-term applications, possibly within 5 years. The established quantum error correction framework, while complex, is proving its efficacy with chips like Willow, crucially enabling logical qubit lifetimes to exceed their physical components. This, for me, is the ultimate proof that the engineering route is valid and progressing.
And from my perspective, the complexity really requires multiple viewpoints to fully appreciate the scaling challenge ahead. While the current hardware, like Willow, is rapidly improving its performance and extending its logical qubit life, yes, the fundamental barrier of QEC overhead and the sheer physical infrastructure requirements remain, I believe, a long-term economic and logistical killer. The ultimate competitive advantage will inevitably go to the architecture that solves the noise problem at its core, allowing the kind of rapid, exponential scaling that only a truly stable, fault-tolerant system like the one proposed by topological physics can realistically achieve.
Both paths certainly represent incredible achievements in humanity's quest to understand and wield the power of quantum mechanics.
Yeah, the strategic choice facing the field, and this is a pattern we see recurring throughout technological history, right, is whether you refine the known path to achieve those near-term gains, or you risk everything on a revolutionary, maybe still unvalidated, new state of matter to secure that ultimate massive scale-up potential.
The answer to this technical debate is really going to define the next technological revolution. And there is certainly much more to explore in the material as both sides continue this race toward true fault tolerance.